Now let's look at some specific GNNs or specific known MPNN architectures. We're going to use the following notation. For a node V, n hat V denotes the neighborhood of V, the neighbors of V, including V itself. Remember that so far NV didn't include V, okay? We also put a hat on the degree, so deg hat is the degree plus 1 plus V itself, okay? And D is a degree matrix. It's a diagonal matrix with the degrees in the diagonal, and D hat is the same plus 1, okay? So it is D plus identity, which is also diagonal, okay? The first model we're going to look at is the GCN, Graph Convolutional Networks, okay? So the idea here is to use a linear transformation, linear aggregation, everything is linear, but we normalize by the node degrees and also apply an activation function, okay? So this is how it looks like. We sum up over the neighborhood, including U itself, so this is a sum aggregation, okay? We use the previous value, hvk minus 1, multiplied by some weight matrix, and then we normalize it by this product of the degrees of the two endpoints of the corresponding edge of the message. Okay, so this is the degree of U times the degree of V square root. Okay, here sigma is an activation function, it can be sigmoid, it can be ReLU, leaky ReLU, whatever. Okay, but applied pointwise. Okay, now you can also write it down in matrix multiplication form. Okay, so you can verify that basically this product of matrices is a one-on-one representation of this semantic representation. Okay, with the neighborhood notation, and here A hat is basically A plus identity, the adjacency matrix plus identity. The next model is GATT, Graph Attention Networks, and here the idea is basically to aggregate the neighbors using attention. We pay more attention to some of the neighbors based on their values. And remember, attention basically means a weighted average, where the weight in the average is defined smartly. So it looks like that. We sum up over the nodes of the neighborhood of U, including U itself. Okay. For each one, this is basically the value, WK times the value of the previous layer, HVK minus 1. So this is our value, and this is the coefficient of the value, alpha U VK. This is a scalar. On top of that, we apply an activation. Okay, so WK is the weight matrix, WK times HV is the value of the node V, and alpha U VK is the amount of attention, okay, which we define next. As in usual attention, we use softmax, okay? Softmax on mat. On some EUK, I'll define it next, okay? This is softmax. But basically, EUK is a vector of length M. M is the number of neighbors of U, okay? And then alpha V1 to Vm is obtained by constructing a distribution out of the EUK. This is a softmax over EUK. Okay, so how do we define EUK? Well, here there's a special variation of attention. Usually in attention, we take the product of the query and the key. The query and the key relate to each other using product. Here, they are used in an additive manner, and it looks like that. This is the query of U, WKHU, the previous value, and we take the concatenation with the key. Okay, this is WK, same WK, H V1. Okay, this is the key of V1, and this is the key of VM. And again, concatenation with the query, WKHU. And to make a number out of that, we multiply it with a weight vector. So it's AK times this concatenation. Gives us a scalar. Okay, again, the neighborhood, including V, is V1 to VM. Oh, this is a neighborhood of U actually. And this O plus is the concatenation operator, as I said. Okay, and AK is the weight vector. And it's somewhat special or limited or degenerated version of attention because WKHV prime, you can see here that it is used both as the query and the key of V prime. And also the weight vector WK is the same is shared basically by the queries, keys, and values. Okay. Now, from an attention layer, you can construct a multi-head attention. Okay. In the usual way, you simply construct H different attention layers, concatenate them, and combine them somehow. Okay, and each layer is using its own distinct, disjoint set of parameters. Okay, so they run experiments on publication data sets and using 2 layers, 8 attention heads. And basically, what's interesting is that when they compare to GCN, they make sure that the two are compared, say, in equal terms. So they make sure to use the same number of features and the same depth, which is 2. And you see that they get better results, at least on Cora and CiteSeer. Here's another network, GIN, Graph Isomorphism Network. Okay, this is basically inspired by the Weisweiler-Lehmann test. Okay, but simple, smooth, differentiable version of that. Instead of the bag, we use a sum. Instead of the hash, we use an MLP. So it looks like that. We go through the neighbors of U. We take their previous color or previous value. And we also add the value of U, okay, from the previous layer, but it is slightly distinguished from the rest of the node. So it's not the value itself, but rather the value multiplied by 1 plus epsilon. Okay, and this is a learned epsilon. Okay, and remember in Weisweiler-Lehmann we have the color of U, comma, the bag of the colors of the neighbors. Okay, now this is motivated by some theory showing that such a function with the MLP over this sum can actually have the separation power of 1 WL. Okay, and this is a special case of more general statement, known statement about MLPs, multi-layer perceptrons. Okay, and they show that GIN has good performance of classification, even if your MLP, this multi-layer perceptron, is actually a perceptron. It has only one layer. Okay, but to get to the good numbers, they need multiple layers. Okay, so here they run experiments on bioinformatics and social network data sets, and you can see that, well, first they try out their functions with several aggregation functions, the usual ones. Sum, mean, average, and max. Okay, max is a pointwise max. Now, several interesting things. First, you see that the one layer MLP is a good performance all in all. Okay, highly comparable. Sometimes it is actually the winner. Also, you can see that the chain zero without the epsilon, without the learned epsilon, actually performs better consistently than the one with the epsilon, which is interesting because it has more expressive power, but this is about learning, not about the expressive power.